Happy last week of classes, folks. We're in the first part of today, first part of the week today. So this is first class of the final week, and so we are nearly there. Just by way of reminder, PLC 15 is practice problems, and I just chose a couple of the practice problems, and gave a couple multiple choice questions as to what the answers to a couple of those are. I forget which numbers they were. So that's in a quiz format as it normally is. There are only a couple problems that I selected, so I didn't select every single one of them, just so you know that. And then homework 9 is posted, I think. And that is not something you need to turn in. All right, so this is not for turning in. Okay, we can talk about the final here. It's going to be next Wednesday. The final celebration is Wednesday the 28th. And will essentially be the same type of format as the two other celebrations. You pick a time during the day, and you'll need a fairly significant chunk of time because this is approximately double what a normal celebration would be. So I usually give you 2 hours for that. So I guess I'll be giving you about 4 hours for this, which hopefully should be plenty of time. And it will comprise 50% material since the second celebration, which means special relativity, the Bohr model of the hydrogen atom, photoelectric effect, Compton scattering, the Schrodinger infinite well solutions, how to draw wave functions, which we went over last time, and brings us up to today. And so if you look at homework 9, I've tried to anticipate most all of those things and give you some practice on all of those problems, as well as a couple of other ones. And so I think today we'll manage to get through some of the laser material, and then we'll probably spend a little bit of time on radioactivity in the end of the week. All right, so those, let me just see, I'm just looking at the homework, yeah. Okay, so those problems are, I've anticipated, so we'd be covering those. Should we not cover these things, then I would suggest that we not have them on the homework and they wouldn't be of any use. I put them on there thinking that we will cover them. So this is our situation. That's 50% the new stuff, 50% all material since the second celebration, 50% material, everything up to the second celebration. So that's kind of your, celebration 2 is kind of your cutting off point. So everything before that included all of the stuff on thermodynamics that we started with, including the laws of thermodynamics, first and second, specific heats, latent heats, conductivity, convection, and radiation, as well as the ideal gas processes, the ideal gas model, heat engines, entropy, and then going into ray diagrams, lenses, mirrors, reflection, refraction, Snell's law, internal reflection, and then going into waves, path length difference, interference, and wavelength reduction, and reflection phase shifts, thin film reflections, diffraction gratings, and single slits, double slits, and circular apertures. I think that's pretty much it right there. So everything up to is half, everything post is half, and the cutoff line is the second celebration. All right, so we'd say it's 50% new, 50% old, and that's the balance that I'm going to be shooting for. Okay, so that's the situation in the final. If you are around on campus on Tuesday, which is the day after Memorial Day, so next week, in case you're not aware, Memorial Day is Monday. So Tuesday we'll start finals week. We'll have a live review session here on campus between the hours of 10 a.m. and 1 p.m. and that'll be in room 804. So if you're interested to join that, you may. The live class will also be joining, so it'll be the same thing here. So that'll be on campus Tuesday, 10 a.m. In room 804. So if you are local, you are welcome to join that. Alrighty. Okay, so that's kind of the mechanics of what's going on, a little bit of the administration there. In terms of material things, what we've got going on, we talked about how to guess at what the wave function looked like for different potentials. So this was kind of based around the Schrodinger equation and the situation that I gave you for the infinite wealth. So when you look at the homework problems and homeworks at 9, think about starting with the infinite well. So just to give you a little bit of a recap on what that means and how to work with that, let me just take a few minutes right now to do that. So this would fall under the idea of sketching the wave function. And I gave you a couple of mentality points to think about. And so number one, when you square the wave function, you're talking about probabilities. That's a measurable thing, so we should have some physical intuition about this. For example, do we expect the particle to be here or not here, or over there, or not so much over here, or more over there than it is over here? Hopefully that's something that we can develop a physical intuition for. Because that, after all, is a measurable thing. Another thing to think about is the number of peaks in the wave function is related to the energy in the wave function. Okay? And that's kind of down to the idea that the wavelength of the wave function is related to the momentum, and the momentum and kinetic energy are similar. All right? So this also comes from lambda going to p, and thinking about, oh, I've got more energy, I've got less energy, and I can tell by the number of peaks. This was the one I got wrong last time, and the amplitude, mostly, I got off on the wrong foot on that one. The amplitude is indicative of the probability, okay? But the amplitude will be higher in places where there's lower kinetic energy because of time spent there. All right? So the amplitude is larger with less kinetic energy. All right, so in places where there's less kinetic energy, you would imagine that there should be a longer wavelength, but also a larger amplitude. So you're stretching the wave when it has lower kinetic energy. You're stretching it this way with wavelength. You're also stretching it this way with amplitude. You want it to be continuous. So the wave function should join pretty smoothly to other parts. There, like I was showing you last time, we'll go through it again real quick, but the idea is that you join the wave function and it's not a separate thing over here and a separate thing over here and a separate thing over here. It should join smoothly. Especially when you get to places where the potential is infinite. So infinite potential, come on Ben, potential indicates that the wave function will be 0. And finite. In other words, if you have a situation where you're confining a particle with two infinite sides, like we did with the infinite well, then the wave function is identically zero outside the box where the infinite potential occurs. However, if I'm confining it with finites, okay, and finite potential, so if that means I have like a barrier like I had last time in the middle of a well, or one half of it's got a finite barrier on it, I have to look for the wave function being proportional to e to the minus alpha x, or something like that, okay, for exponential decay. Because physically, we and I'll put the x in absolute value, so it goes both sides. We expect the wave function to decay exponentially out, indicating we don't have much expectation of finding a particle with a total energy that's less than that potential step to be outside of its area. Right? This is a finite potential. It should look like that when the total energy of the particle is less than V naught, which is the step height. Okay? If it's greater than V naught, then we should go back to the normal oscillating solutions. So where V is constant, whether it be zero or a constant step, then we would expect oscillating solutions, which are standing waves. Let me write standing waves instead. I think it's a lot nicer. Standing waves. And that means we're looking at psi being something like A sine kx plus B cos kx. Or something along those lines. Okay, so a list of things to think about when you're drawing. When I looked at the wave function last time, in the potential of the infinite box, okay, I had the potential of the infinite box here up to infinity on both sides. And we had a step in the middle, like this, of height V naught. This was zero. And so we were sketching it for the situation where the energy initially was down here. And that's a situation where the wave function would be oscillating where the potential is constant. But then over here, since the energy is less than V naught, it's decaying exponentially. And over here, the potential is infinite, so it's going to be zero identically outside of that. Right? That means that my wave function for this, if I just graph it here, like this, I have wave function of zero right there. This is the middle point here. Then I know that the wave function is zero here, and therefore it starts off looking like a regular infinite well. In other words, knowing what the spectrum of wave functions looks like for the standard infinite well is going to be very useful. Knowing that you have a jump rope pattern or a full sine wave, etc., etc., and knowing that you go out further and further sine wave half wavelengths for every step up, that's a useful thing to kind of know that this is what the set of wave functions looks like, because we are basically taking those and modifying them with these. All right? So in the case of this, what we were talking about was starting at zero and then going up like this and then decaying down like that, and then reaching into zero like this. So one wave function that would be a very low ground state energy would be one in which I have just a single bump in the middle. But when it hits the halfway point here, it doesn't just drop to zero, it decays exponentially and comes down. Definitely has to be zero by the time you get to this boundary out here on this side. And it hit zero pretty quickly over there anyways. Okay. If I go to a situation where I've got a total energy of the particle which is up here, then the wave function for something like that is going to be of one particular wavelength on the left side, a different wavelength on the right side, and the amplitudes will also likewise be different. With lower kinetic energy here, I should have higher amplitudes, which is the thing I messed up last time because I was thinking backwards. And it's just that time of the semester, you know. Fortunately, we got that straightened out. So, anyways, the rest of this we did last time, so I won't go through it again. But just thinking of these steps as you go through to draw the wave function for different potentials. I think we also talked about the one in which I mirror reflected this entire thing around like this and had a low part here with two finite steps on either side. Same basic ideas. And what would happen is you think about the symmetry of the wave function. The wave function would be likewise mirror symmetry. So that's one other thing I'm going to put on the list here, symmetry. Thinking about what does the wave function look like if I mirror reflect the potential or I mirror reflect the wave function. Okay, anyway, so that's pretty much what we have there. I give you a little bit of practice on the homework, so take a look at those and see how we go. All right, let's move into talking a little bit about lasers. I'd like to spend a little bit of time going through the development of the laser from a theoretical standpoint because it's really not what you would expect. Well, maybe it is. I don't know what you would expect, but it was a pretty strange thing when I learned about it. Laser itself is an acronym. And so it's not actually a word. It's become a popular word. And the acronym itself is not totally forced either, which is kind of a fun thing. If you already know the acronym, then I guess this is going to be review for you. Alrighty, so the acronym starts with light, and it's basically light amplified, which it is. The light's amplified, because when you look at a laser beam, there are a couple of things that should stand out to you. One of them is it's basically almost just a beam. It's not a ray, but it's a bundle of rays, right? And they're all traveling in the same direction. It's also extremely intense. So the light is amplified. It's light amplified by what process? The process is known as stimulated emission. It's the stimulated emission of radiation. Which, of course, it's the stimulated emission of radiation. That's what gives you the light. The radiation is the light. Historically, just from a chronological perspective, in fact, the laser was not invented first. The first thing that happened was the maser. And the maser is microwaves amplified by stimulated emission of radiation. And they didn't then get to making the laser until a couple of years later, maybe not quite a decade, maybe about 5 years, 5 to 6 years later. The visible wavelengths were part of this. So, the visible light laser is about 1961, I think, by a fellow by the name of Ali Java. And he got this to work. It was basically, he invented the helium neon laser. So let's talk real quickly about laser light qualities, the characteristics of laser light. That didn't work out like I wanted. Characteristics. Okay, good enough. Close enough. Laser light. So as I mentioned, it's very what you might call unidirectional, right? It's all kind of, it's a beam. It's going in one direction. It's very thin. In other words, it's collimated. unidirectional. It's, interestingly, this you can't see, well, actually, let me do this first. It's monochromatic, but that's not 100%. It's very monochromatic. It's not 100% monochromatic. Monochromatic meaning single colored. In other words, almost single wavelength. And to some lasers, that's a very good description of it. It really is very, very close to being just a single wavelength. Now, why it isn't, we'll get to a little bit more on why that is, but monochromatic, right, single wavelength. Describing the entire beam. And so it's collimated, meaning it's thin, it's like a pencil beam traveling, it's in single direction. It doesn't have a lot of spread. It does spread out because it diffracts through a small opening, right? So, for example, what we do is we use a laser rangefinder on the moon. The moon, this is a great piece of, a couple of bits of physics here. On the moon, we got there due to gravitation, so that's kind of cool. When they got there, they installed a corner cube, which is two plain flat mirrors making a 90-degree angle with one another. And if, for example, you have studied mirrors that are at an angle with one another like this, you might know that if light is incident on one of those mirrors, it will bounce off to the other mirror and then return exactly opposite to the direction it was incident on the first mirror. So if these two mirrors are at 90 degrees, then the angle is the angle of light travel is 180 degrees. In other words, it's completely reversed. And if you've ever been to a fancy clothing store, they will typically have a corner, two mirrors in a corner like this, so you can look at yourself. And then you'll see three images of yourself, because you look at yourself in this mirror, you look at yourself in this mirror, and then you'll kind of look straight ahead and you see yourself again. It's kind of cool. Anyways, they have one of those on the moon. We shine a laser at it, and the laser bounces off and comes back and tells us how far away the moon is, because all we got to do is go, okay, hit the laser, and start the stopwatch, and hit the stopwatch. And by the time the laser light comes back. Now, by the time the laser gets there, though, because it has spread out, it's diffracted through the circular aperture of the laser beam, of the laser opening. By the time it gets to the moon, it's like really big. I forget what the diameter of the beam is by the time it gets there, but it's like 1 kilometer or something. It's huge. Anyway, light takes about a second travel time to get there, and about a second's worth of travel time, a little more than 1 second to get there, more than 1 second to get back. So to range find the moon is actually a pretty quick process. Anyways, long story. Collimated beam, unidirectional, monochromatic, and the most interesting one, coherence. The beam is coherent, meaning that all of the, if you like to think of it, all of the photons that make up the beams are swimming together. They have very long range coherence, on the order of, could be hundreds of kilometers. Whereas coherence from a light bulb is probably over within a couple of centimeters. Okay? So coherence meaning that they are essentially phase locked together. I'll just put same phase. Okay? So, and we'll talk about that because that's a characteristic of the stimulated emission process. So we'll take a look at the stimulated emission process as we get a little further into this. All right, so a couple of characteristics of laser light. We want to be able to describe both a gas laser and a solid state laser. And you know, gosh, I didn't bring in. I should go get the gas laser so we can take a look at it. But let's start off by describing what this looks like, okay? So the helium neon laser is the one that we're gonna look at. This is a gas laser. And I forget what it's made out of. But I think it's got some elements in it
Oh, wait, it's helium and neon. Right. How could that escape me? What they did is they created this mixture of helium and neon, and when you look at a helium neon laser and it's that red color, that's because the neon is, oh, and it is doing the laser action. So here's a great cocktail party icebreaker. So laser, you already know, is not really a word, it's an acronym. All right, so there's first piece of cocktail party trivia. However, if you want to go around the cocktail party and have people start noticing you, take the word laser and make it into a verb or an adjective or something like that, so that you're talking about lasing. If people hear you, they overhear you. If they're walking by, they overhear you talking about the lasing action. The lasing action in the neon atoms is go da 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 da, right? Or in the lasing cavity, we've got multiple reflections for stimulated. As soon as they start hearing words like that, they're going, oh, that person's smart right there. Lasing. Who uses that? Only people who are really smart. So obviously, if you know it, you're smart. So I'm trying to welcome you in here. Lasing. Let's talk about this. It's a mixture of helium and neon. And therefore, it's known as the Heaney laser. Let's graph the energy states for these things. I am going to draw a staircase, but it's going to be a very incomplete staircase. I'm only going to focus on the stuff that we really need for this discussion. I'm not going to draw every energy state. I'm only going to look at the ones that we care about. So here, let's say, is the helium neon. Here's the helium state. Let's suppose we've got a ground state down here. Here's the ground state. Okay, so the helium ground state's down here. And what happens is essentially the exact same thing as a fluorescent light tube or a discharge tube or whatever you like to think of it. We are going to excite these electrons. And so the electrons are going to be passed through the gas with a lot of kinetic energy. The electrons are then going to come flying along, and they're going to hit helium atoms. Okay. When they hit the helium atoms, they can cause, through collisions, they can cause the helium atoms to excite their electrons. Okay. So in other words, an electron comes bopping along, sees a helium atom with its electrons in the ground state, as they always usually are, right? And then, as the electron collides, it transfers that energy into one of the electrons in the helium, which then pops that into a higher state. All right. So through collisions, let's say it's just up here. This is the excited state of the helium. Now there are other states in between here, but I'm not going to bother drawing those. This I think is, let's say this is the ground state. So we'll call this n equal to 1 here. So this is 2, 3, 4. This is the n equals 4 state. The electrons get bumped into that energy level due to collisions with these incoming electrons from the current that we are supplying. All right. So electrons here and gets bumped into there. Via collision. With what I'm going to say here is electric current. Because basically what we've done is we've injected a large number of electrons and we're pushing them through really fast. And essentially it's a spark that starts over here and terminates over here. So the electrons are flying through here, and as they are flying through, they are banging into helium atoms and causing those helium atoms to become excited. Okay, now, the good thing about that particular state in the helium atom is, and this is one of the things that we need if we're going to make a laser, it is a metastable state. In other words, the helium electron that's there, it can survive in that state for quite a bit longer than you'd expect. Typically, and we haven't talked very much about this, but typically, when an electron gets promoted, it's falling back down pretty rapidly. Okay, so it doesn't spend appreciable time in any state, maybe a couple of nanoseconds, and then it's going down, dropping, right? And it's emitting its photons as it does that. However, every now and again, you'll find an excited state which has a much longer lifetime. You know, it could be 4 to 5 to 10 times longer, so that might mean 5 to 20 nanoseconds. It might have an extended lifetime in that state, such that if something were to promote the electron to that level, like an electric current, it will stay there, and then hopefully in the time it's up there, prior to it dropping back down, we can do something with the electron while it's up there. Okay? So this is where the neon atoms come in. Here's the neon atom over here. I'm going to draw its energy ladder over here. Again, I'm not going to draw all the states, just the ones that are of consequence. So here is neon ground state down here. And there's a set of states right here, which I believe this is the 1, so this is 2, 3. Here's the 3 state right about here. This is the 3 state, and then this would be the 2 state right about, say, here. And so in the neon, what happens is, as with every other atom, typically the electrons reside in their ground states. That means that they are, remember with the uncertainty principle giving us the idea, the electrons are as close down to the nucleus as they can be. And that means we could spend time talking about filling of electron shells and all that type of thing, but I don't think we're going to have time for that. Nonetheless, the electrons are as low as they can be. Now, neon has 10, if I'm not mistaken, and therefore, when I say ground state, I'm really thinking about the entire distribution of all 10 of those electrons. They are all in their lowest states that they can be in. That doesn't mean they're all in the smallest n=1 state, but there is a way to describe all of the electrons in neon such that the entire atom is in its ground state. Okay? Now, what we're going to rely on, and neon is a very much larger atom than helium is. Okay, so helium now has this metastable electron in its excited state, and what's going to happen is, very strangely, these two can actually collide with each other. And rather than have the electron drop down to its ground state and emit a photon, or you could imagine that this is actually what's happening anyways, typically we just talk about it as a collision, whereby these two things, a helium atom and a neon atom, actually bonk each other, just the way that the electron got the helium atom excited. The helium is going to take the electron energy that it has here, and it's going to transfer it into the neon. So how it does that, okay, well, you can imagine it colliding, and this electron drops, but instead of giving out a photon, or if you like, that gets absorbed by the neon. Now, the reason that I'm a little bit hesitant to say you can describe it as a photon process is because these energies, if you look how I've drawn them, there's a slight difference here. Okay, the helium state is a little bit lower than the neon state. And so what actually we need is not just the helium going along and hitting each other, having the helium go along and just knock into a neon. It's not going to touch it and give up all its energy. It has to actually be moving. So the motion of the helium atom itself gives the rest of the energy that we need in order to get an electron bumped into the 3 state up here in the neon. Okay? So the key piece here is that we've got this helium in a metastable state. It can transfer the energy of itself into an electron in the neon. So this bumps this electron up. This is a transfer of energy here. It transfers the energy here and causes this electron to jump up here. Now this one has jumped back down and is no longer up there. All right. Now the neon state, that electron's up there and it's saying, why am I here? What am I doing all the way up here? Why can't I be down in the ground state where I would prefer? I can be down next to my cousins, and this is where all the action is. Why am I up here all by myself? So what we have here is then a neon electron which is trying to drop back to the ground state. It does so by transferring from the 3 to the 2 state. When it does that, this is where the lasing action occurs. See what I did there? As the electron drops from here to here, out comes a photon. This photon has a particular wavelength, and it is the red wavelength in neon. It has a very well-known wavelength. Because after all, as I said, this is single wavelength light that we're looking at. Mostly. Okay, so we take a look here. I'm just going to make one note over here that this is metastable. In other words, it's got a slightly longer lifetime. Not that it's stable. It's not stable. Not like you'd put the electron there and it would stay there for as long as you want. It'll stay there for a little bit longer, and then it goes. That's what metastable means. Now, when this photon gets emitted, this has a particular wavelength, and that happens to be 632 nanometers, or 633. Really, it's like 632 point something. So that goes in here, and it drops down. Okay. Now, we have not yet talked about laser action. But the lasing photon, this is where the laser, this is the laser photon right here. This is the laser photon transition, okay? We now have to describe the lasing action which occurs due to that photon being emitted. But I first wanted to at least get you to understand how the electrons get to these states and what qualities we need, all right? So the transfer of energy occurs from the helium to the neon, typically via what we say is just via bumping it, just via collision. Okay, because the helium atom itself carries a bit of kinetic energy, and that helps get over this slight energy difference in the states. Okay. Okay, so it transfers the energy via collisions. It bumps the neon electron out of its ground state up to here. That electron then decays into the 2 state, and then it goes into the 1 state, and nobody really cares about that. That's another photon, whatever, who cares? What happens is it then drops down, a helium atom then hits it, and it does the same thing all over again. Okay. Now, what you can do is one of 2 things, I suppose. You think about this happening in another neon atom, okay? And the other neon atom has its electron up here. Now, when does the electron decide to drop from the 3 to the 2 state? Well, that's a quantum mechanical probability issue, right? When is it going to happen? We don't know. That's like asking when is a nuclear decay going to happen? When is this nucleus going to blow up? We don't know, but there's probabilities that we can talk about, okay? So the same is true here. I've got a situation where I know there's going to be a transition, I just don't know when. Okay, this is the key right here, this emitted photon. How do you get lots of these all at once? Well, it's via what's called the stimulated emission process. So stimulated emission essentially means that this photon that's coming out is going along and is going to hit another neon atom that's in exactly the same situation as this one was before the photon came out. I'm going to draw that other neon over here. Here's another neon. And here I've got the 3 state, and there's an electron in it. Here's the 2 state, and the ground state somewhere down here. Oops, down here. And we don't really care too much about that because that's not visible. So now we've got, this is in an excited state right now. Okay. Now, as this photon comes past, it jostles this electron. What happens, in other words, is this photon that was emitted by this transition here. This photon comes along. I mean, how do you want to think of it? Well, the photon is what? It's a disturbance in the electromagnetic field. It's a quantized disturbance in the electromagnetic field. That is traveling here, and because the electron has an electric charge to it, the electromagnetic field is how the electron talks to other things. So basically, this photon, this disturbance in the electromagnetic field, comes propagating over, and this electron feels it. So the way I think about it is, for example, if you're stuck at a party and you're kind of like, this is totally not a good scene for me, and you've gone with a friend or two, and you want to get their attention, but you don't want to be like, hey, let's get out of here. This place is terrible. This is no good. You don't want to shout that across. That'd be offending the host. So what you want to do is you want to be subtle about it, right? So you want to walk along and you want to get near your friend and you want to go, hey, give him an elbow and let's go. Well, right? Everybody knows that. Right? Elbow, head, off we go. We know what we're doing. As soon as you see that, you know exactly what you're doing. Basically, this photon is doing the exact same thing to the electron. It's going along, it's going, hey, let's go. Gives it a little elbow, come on. And go, there's a photon in there, let's get it out of there, all right? Now, what happens? The photon comes by, elbows the electron drops because it's like, uh-oh, right? That's like having something once again in a metastable situation whereby any little pop will cause it to fall over. So this is the little elbow that it needed in order to go, clunk, and it drops. This is the stimulated emission. In other words, it's because this happened and we emitted a photon out of there, that photon now causes this one to drop. That's the stimulated emission. It's the elbow that this photon gives to this electron in order to make it pop down. When this electron drops down, it of course emits a photon. Now, this one is going along, but now it also emits, because this was a drop, and it emits the exact same photon as this one did. So note, the original photon is not disturbed. It was just going along and it gave a little elbow to the electron. It didn't do anything. It didn't absorb. It didn't scatter. It just popped it. And so the electron dropped, and now the original photon is there, plus the one that this electron now emits. Okay? Same exact photon, lambda 632. I should probably say 633, but whatever that is. All right? That's the stimulated emission process. It's this photon hits an excited atom, which causes it to decay and emit a photon of the exact same character. All right? So original photon basically goes through and nudges this electron. It causes the electron to decay, and therefore in the decay it emits the exact same character of photon. I'll just call it an identical photon. But notice now what's happening. Oops, photon, not photons. Okay, so notice now what's happening. I had one photon, and now I have two. Each one of those photons is going to go do the same thing to the next neon atom in line. So each one of those photons will now produce two. That means I'll have 4 photons. Each one of those will go through and make another photon. So now I'll have 8. Do you see what's happening here? Every generation, it's doubling. Okay, started with 1, went to 2. 2 became 4, 4 became 8, 8's going to become 16, 16's going to become 32, 32 becomes 64, blah, da, 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 da. We have a name for this. The name is a chain reaction. This happens to be known as a doubling chain reaction. So it causes this cascade chain reaction inside the lasing cavity. See what I did there? And when you do that, you are able to then get a very intense beam. Now, notice, the stimulated emission causes, I didn't draw it up here, but I will say this other last piece about that. The stimulated emission causes the emission of a photon at the exact same point in its wave as the one that elbowed it. So if this one comes out like this, that's because this one was doing this. Okay? In other words, these two photons are swimming totally in sync with each other. They're phase locked, if you like. Okay? That's where the coherence comes from. It's part of the stimulated emission process. So when the photon that is emitted comes out, it comes out at the exact phase of the one that elbowed it. All right? So the original photon causes electron decay and emit an identical photon at the same place in its phase. I'll put this same phase. That's where same phase comes from. That means coherent. Okay, so that's all you really need is a bunch of neon atoms with electrons that are pumped into their higher level by the heliums, right? And what we then do is we put a mirror right here. So these two photons are going to bounce off the mirror, go right back into the action. They're going to go by, elbow another electron, cause another photon to get emitted. Elbow each one of those, elbows one, causes 2 more photons, elbows 2 more photons, 2 more photons. I'm going to put another mirror over this side. So now they hit this mirror, come right back. Okay, so can you see this is kind of my lasing tube? See what I did there? By the way, that does not get old, just in case you're wondering. So I've got the photons sloshing back and forth in here. And every time they're going back and forth, they're making more and more of the exact same photons. So all I have to do is continually supply the energy to get the helium atoms pumped into this high state here so that they hit the neon atoms and cause the neon atoms to be in this excited state. None of this would be possible without the neon in the high state right here. Right? Because it's the neon decay that is the essential, this is the essential character, this is the essential action of the laser. It's this transition right here. This is the lasing transition. So if I don't have neon atoms in the upper state like this, I don't have a laser. What we need to do then is continually pump the helium atoms up into this and have enough of them to bump into the neon atoms such that the neon atoms are almost always in this upper state. Because as soon as they decay down, this state is not metastable, the 2 state is not, and it'll decay straight away off here. At which point another helium atom hits it and it's going to go straight back up to here. It's going to then get caught by one of these passing by photons, drop, chain react, emit another one, drop, get bumped, up it goes. So, right, it's just this kind of cycle of continually stimulating the emission, excuse me, of the excited electron, right? And that's what it is. And now you'd say, all right, how do we get the light out of here? Fine, I'm going to make this not completely reflecting. Make this a 99% mirror so that it lets out 1 of every 100 photons. We can do that, right? That's just like it's not a half silvered mirror, it's a 99% silvered mirror, so that the beam that's coming out is actually only 1/100th of what's going on inside here. Okay, and that's how a laser works. I want to talk about, so that's the stimulated emission process. By the way, the stimulated emission process was first described by Einstein. If I'm remembering correctly, and I think I am, the process of stimulated emission was first, I think, discovered in about a little before 1920 by Einstein. And people say, oh, he didn't like quantum mechanics. Well, he did a lot of work in it. In fact, he discovered how to do all of this. One thing you might ask is, well, how does this process happen? What causes the quote-unquote first one? Well, chance, right? Just random chance. So in terms of stimulated emission, this first one is not technically stimulated emission. It's natural emission. It's spontaneous emission is what that's called. It's spontaneous. So how does this happen then, you might wonder? Because this one gets elbowed by a passing photon. Well, this one does too, but it's a random fluctuation in the electromagnetic field that does that. So while we're talking about spontaneous emission, do any of the other ones spontaneously emit? Yeah, of course they do. They totally do. But we have kind of saturated the entire field with all of these other photons that stimulated emission actually comes out to be the much more dominant mechanism by which the electron decay happens. All right. So essentially, this is how this happens. The energy between the 3 and 2 state is just hc divided by this wavelength, and that works out perfectly. And you get this wavelength out, and that one stimulates another one to decay, which stimulates 2 more, which stimulates 2 more. So you get all these photons, and that's great. So the thing I wanted to concentrate then on was the atoms themselves. How do we maintain these population, what's called inversions? The population inversion is the situation in which the neon atom is not in its ground state. Now, a typical atom, if you just walk down the street and you interview your typical atom on the street, it'll be in its ground state because there's no reason for it to be excited. It takes energy, it takes effort for the atom to remain in an excited state. Why would it do that if it didn't have to? So typically, these electrons try to drop as quickly as they can. Now note, they can't always do that. They've got metastable states up here. Right? So there's metastable states actually here and here. You can make that. This is also a metastable state. Okay? So you can have electrons residing in these states for slightly longer than normal, but once it drops into this one, then it drops into that one like almost right away. So there's no reason for an electron to stay there, but if we can get most of the neon atoms to be in this state, then we will get a very good laser. How do we get most of the neons into that state? By continually causing the helium atoms to be in that state and then bumping them. So what you need is a mix of the helium and the neon such that you have a fairly good amount of helium in there. Typically more. I think it's more than the neon atoms, such that it's not just a one-to-one transfer. You can always kind of count on an excited helium to be somewhere near a neon atom. And that neon atom will then accept the energy given to it by the helium atom, raise its electron up, and then cause the stimulated emission process. Okay? I will show you a little bit more on how to figure out the population inversion in a second. We'll do a hypothetical situation. I just want to go grab a helium neon laser so you can look at it real quick. So bear with me for just a minute while I do that. Okay, so this is a helium neon laser. It's not going to be super easy to see because of the blue cover, because that doesn't come off very easily because they don't want you putting your grubby hands in here. But notice you can see in here there's a tube. Okay, the tube here has a metal end, and over here it has the other end, which is where the electricity kind of is coming in from, and then this you can't really see the mirrored ends here. But if I do this, which is called plugging it in, you'll be able to see what I'm talking about. Now, the laser radiation, of course, is emitted from this one. Now, if you look carefully into that one, you can see the mirror in there. You can kind of see it in the very middle. There's a mirror in there. It's hard to see because it's so small, but nonetheless, that is the mirror that is causing the stimulated radiation to bounce back and forth. So here's what we're going to do. If I turn this on, I want you to notice two things, all right? So here's the laser turned on. There's the laser beam. It's not impressive from this perspective, but for me, that's a very bright red. It's actually quite hard to look right at it for an extended period of time. So the laser light is a very deep red, and it just doesn't seem to be coming through very well on the camera here. But notice here's the tube. Okay, and if anybody walks through that door right now, they're going to get a laser right in the eye. So here's the tube. Now this is not the same color as what you're seeing from the laser beam. Okay, the laser beam, yeah, see, I'm thinking that you're not going to see the difference here because that spot is not showing up as what I would call its true color. But anyways, that laser beam is this 632 nanometer, whereas what we're seeing here is not, basically, right? So we're seeing radiation that's getting emitted this way, not this way. All right, so what we have here is the laser tube. There's actually another tube inside the big tube here, which I don't think you can quite see, but nonetheless, there's another tube in there, and then a lot of the electronics just hooking up, and then of course we have that big cavity up the metal part of it up here. But inside that tube, that's where all the neon atoms are getting pumped by the helium atoms right now. So there's that. I brought in a few blocks to give you the idea of the metastable transition. This is an electron. And once it gets up to this state, right? So suppose that this is the 3 to 2 transition in the neon. Okay, I've got the 3 state and the 2 state. So once the helium atom bumps it and the electron comes up here, and it's waiting around, right? So it's almost the same as the question of how long can you hold this such that the ball doesn't fall off? Well, it'll be not so much longer, and then all of a sudden I'll be like, oh, I can't hold it, and then off it goes. In doing this transition, I get that particular photon out, right, as it drops this way. Once it does that and it drops off and goes back to its ground state, it is almost immediately hit up and whoops, and then comes up back up here and does the same thing all over again. All right, so a little bit of visual there for you. All right, Let's talk about the population inversion in the neon. I want to go over here. And let's talk about this. So the neon has to have what's called a population inversion. The population inversion refers to the idea that most of the neon atoms are in their excited states, rather than being in their ground states, like I was telling you about atom on the street. It's going to be in its ground state. Most atoms, when you encounter them, are in their ground states. There's no reason not to be. When you supply energy and they bump up to this state, sometimes they'll hang out there for a little while, like these do. Sometimes they'll just decay immediately, okay? So here we're able to cause a particular transition. Now, let me ask you this. Is every single time the neon electron going to go 3 to 2? No, it's not. It's going to be encouraged to do that by the stimulated emission of other photons. So in other words, remember I told you we saturated the tube with these photons. So the likelihood of it dropping 3 to 2 rather than 3 to 1 is much greater. So that transition becomes suddenly a very more probable transition than straight to the ground state. All right, so usually, so population inversion neon means most neons are excited. All right, so usually atoms are in their ground states. And it was a fellow by the name of Ludwig Boltzmann who put together the idea that what's the probability that something's going to be in its excited state? So if I have in state X here, or state 3 in this case, the population in state 3, the number in state 3 divided by the number in the ground state, is essentially how likely is it that that energy got supplied to the atom in order for it to bump up to that state. This is an exponential that relies on the energy difference between these two states. So in other words, it's e to the negative E3 minus E1 divided by KT. All right, this is called the Boltzmann factor. And what it does is it relates the ratio of the energy needed in order to get a atom to go up to this state, and it takes that energy and it ratios it by how much thermal energy is there. Okay, so in other words, this is a way of describing probabilistically, just randomly, what's the probability that these atoms are going to be in their upper states. So if you know about dying exponentials, you know they die pretty quickly, usually. And at room temperature, just to give you an idea, the value of KT is about 1/40th of an electron volt. So KT at room temperature is approximately 1/40th of an EV. In other words, that's approximately 0.025 EVs. In other words, that's how much thermal energy you would get, or an atom would be able to attain just by being in a room of about 300 Kelvin. Okay? Therefore, you can see it's probably not likely that this transition is going to take place due solely to a thermal excitation, right? If this E3 is significantly far above, and typically they mostly are, right? Then this is really not a likely thermal transition. So we have to be clever about it. That's why somebody found out about using the helium atoms to go transfer energy to the neon atoms, okay? Because this process is typically not going to happen naturally. Typically. I didn't say never, I said typically. So let's cook up a quick example here in which I have just take a two-state atom. Okay, just forget about all this stuff for a second. Let's just look at a hypothetical two-state atom and a normal distribution of atoms. A normal distribution of the electrons. So suppose I've got 10 atoms here. Okay, so the normal distribution would be something like this: 1, 2, 3, 4, 5, 6, 7. 8, 9, 10. Okay, normally they're going to all be sitting down here. Does this say that the probability is 0? No, it doesn't. Okay, but it's the delta in the energy. So suppose that since we're only dealing with a two-state atom, suppose that now I'm dealing with 2 to 1 here. So this is 1 and this is 2. So the energy difference is really 2 to 1, and you can think of this as being, for this situation, this is state 2 and this is state 2. Okay, I had written that for the neon atom, but now I'm going to transition and go to this hypothetical state where I got only 1 and 2. All right, so this is a normal situation. Here is the inverted situation in which you're probably not too surprised to find that it's the exact opposite. It's literally inverted. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so this is this is a population inversion. Okay, 1 is my ground state, 2 is my excited state. All of these ones are in the second excited state. How are they doing that? It's not too likely, but let's suppose that when an electron drops, it emits a wavelength of 550 nanometers. Okay, let's assume it emits a nice green. Okay, so I can calculate the difference between the energy states. Okay, that means that the delta E is hc over lambda, and that's 1240 divided by 550. So I picked stupid numbers here, but that's the way it goes. All right, so that's some number that's like 2 and a bit-ish, because twice that would be 1100, so say I need another 100 on top of that, so it's 2.2 EVs, say, all right? This is probably not terrible, 2.2 EVs. Okay, so that's the difference. If these electrons, when they drop, emit that wavelength, then that must be the difference in energy between these two energy levels. Now, if I want to figure out what's the likelihood of a population inversion from the Boltzmann factor, what I would do is say, okay, I know what the energy difference is between the two energy levels. It's 2.2 EVs. I'm going to now divide that by 0.025 EVs. And I'm going to put e to the negative that thing. This is going to be a horrendously tiny number, right? This is 2 divided by, or 2 multiplied by 40, essentially. So this is e to the minus 80. Almost e to the minus 100. That's a number that is horrendously tiny. Like 10 to the minus 20 or 30 or something. Maybe even 10 to the minus 40. Well, whatever it is. It's really, really, really small. Okay? So when you look at a population inversion happening spontaneously, that's almost 0. 10 to the minus 30th. You're like, yeah, that's not a big probability of happening. I'm not going to have this happen naturally. Could it? No. Yeah, one time in 10 to the 30th, but it's not going to typically happen, all right? So that's what it means to say that we need to come up with a different way of of getting that energy transferred so that this inversion happens. Okay. Now, suppose that we have a cycle, and we know that we can, once they decay, we can pump these things back up within, 10 to 20 nanoseconds. Okay. And we can pump them back up, they'll fall back. I'll pump them back up, they'll fall back. Pump them back, and fall back, so that I can estimate about what the power is. Okay. If I know that this is a 2.2 EV transition, and that's going to happen every 10 to 20 nanoseconds, right? So I can divide that and say, well, how many photons am I getting out per time? How much time happens, right? Am I talking about nanoseconds between each one of these, right? So now you can start relating the energy of the photons to the number of photons and how quickly they cycle back, and you can start relating that to the power of the laser. All right. So maybe we'll pick up with that starting tomorrow. Just doing a quick example on how to find the power of the laser based on the photon number, like the number of decays, and the wavelength, which leads to the energy difference between the states and the cycle time. We can try to get a laser power out of that. All right, so we'll talk a little bit more about lasers tomorrow. I'll introduce the solid state laser and how it's different from the gas laser. And then we will go into some radioactivity, and that'll be tomorrow. I guess Thursday we'll do a little radioactivity. I'll probably reserve a little bit of time just to do a summary of topics for you to look over prior to the final celebration. And then ultimately after Thursday, that's it. I still have not received everyone's lab kit back, but thanks to those of you who have returned it, really appreciate that. Again, we are going to be running this class in the summer, and therefore we need every lab kit back in order to not have to buy more lab kits with money that we actually don't have to spend on that. So please, whenever you can, either drop it by campus here in room 802, typically between Monday and Thursday. Julie is here, say about 10 till 4. On Thursday, she's typically here till maybe 5 in room 802, our physics lab room. If that's not going to work, please send Julie an email, and she will respond with the shipping address if you are not going to be in town to ship this. So please, let's try to make this happen and give us those back so that we can use them in for future students, okay? Alrighty, so at this point I will say happy day and good luck. See you until next time. I'll see you next time. How about that? Alrighty.